Hi guys, these are your notes for Chapter 11, Section 1 on Introduction to Polynomials. I think you're going to know a lot of the stuff today. It's going to be a lot of vocab. Not difficult, but you might want to take some notes so that you have it handy in case you're looking for what a certain word means. Okay, what we're going to talk about today is a polynomial. Polynomial has the root poly, which means many. It's going to have many pieces. If you remember, a monomial was just one piece, like 2x, 3x squared, y, z to the third. Just one piece, one piece. Polynomials are going to have a plus or minus sign. So if I take these two monomials and add them, all of a sudden this becomes a binomial, which is a polynomial because there's more than one piece. Okay, here is an example of a polynomial with just the variable x. Okay. The largest exponent is going to be the degree of the polynomial, and you're going to be asked this a lot in your future as a mathematician. The degree of a polynomial is very important because it's going to tell us some qualities about the graph. For example, you guys know that if you see something with an x squared, that the graph is going to be a parabola, and we've seen x to the third, the graph is going to be one of these guys. If you know what the degree is, you have some hints, not exact science, but you have an idea of what the graph might look like. So in this example here, 4 is the degree because 4 is the highest exponent. You're going to look for the biggest exponent. This is called standard form because it is in decreasing order. 4, then 3. There's no x squared, so they skipped it. Then x, and then nothing. If it's in standard form, it'll be right at the front, but be careful, it's not always going to be in standard form, so sometimes you have to look. You're looking for that highest exponent. That is your degree. Each piece of the polynomial is called a term. So this one has 1, 2, 3, 4 terms. 1, 2, 3. We're going to include the negative sign with it, and 4. Okay, here's a definition of a polynomial, which isn't going to make a lot of sense to anybody. Basically, they're saying if it's in x with degree n, they like you to start with your biggest exponent. This a sub n is just some constant. So a constant, 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 just some number. X is always going to be there, and then preferably the exponents are in decreasing order. Oh, it says right here, n has to be non-negative. We can't have negative exponents. If there's a negative exponent, it's not going to be a polynomial, okay? We want positive exponents. Standard form, like I said, is when the polynomial is written with the highest exponent first and in decreasing order. Coefficients, you know what coefficients are from the quadratic formula. That was the a, b, and c that we plugged into the quadratic formula. It's the numbers in front of the variables. And the leading coefficient is the number in front of the variable that has the degree. Okay, so if you find that biggest exponent, the number in front of that will be your leading coefficient because it would be in front, it would be the lead or in front if you were in standard form. And we like them in standard form whenever possible, so that's why they call it the leading coefficient. And the constant term, or just the constant, is just the number at the end. There's no variable. That's important because it tells us a lot about our y-intercept. Okie dokie. Lots of words. Here are some special polynomials. I think you know them. I'm sorry about the way this kind of ran off here. A linear polynomial is if it's in degree 1 because when you graph it, guess what it is? A line. Okay, we saw this guy already this year. Ax squared plus bx plus c. We call that a quadratic. Cubic is if it's to the power of 3. Quartic and quintic, to be honest, I don't usually call them quartic and quintic. I call it a 4th degree polynomial or a 5th degree polynomial. But the technical term is quartic and quintic. When the degree is 4, the degree is 5. After that, we just say a 6th degree polynomial or a 7th degree polynomial. Okay, they're graphs. All polynomials are functions, okay, because you can plug anything into them and you'll only get one output. So everything we plug in, we'll just get one output. Therefore, by definition, they are functions. We can graph them. If you graph them, it will be a smooth curve. Okay? Linear and quadratic polynomials give us clues as to what the graphs will look like. Higher degree or more difficult, we will talk about them some this chapter. Okay? If it's a linear, it's going to be a line. If it's quadratic, it's going to be a parabola. you will start to learn tricks about what the graphs will look like just by looking at their equation as you progress through your math classes. Okay, we are going to talk about some things we can do with polynomials. You can add them and subtract them and multiply them. These are things we've done before. So the first thing we're going to do here is we're going to evaluate each expression and see what happens. So let's start with adding. This is a quadratic polynomial, and this is actually a cubic. Okay, we are going to take f of x plus g of x. All you do when you take f of x plus g of x is combine like terms. So I'm going to write it out here. 2x squared plus 3x plus 4 plus 5x to the third plus 1. If I add them, I'm going to put it in standard form because it tells me to right here. So I'm going to start with the biggest degree, which is third degree. Then I'm going to go to the squareds, plus 2x squared, plain j and x's, plus 3x, and the constant is going to be 5. You can add them very easily. You can subtract them just as easily, but there's a mistake that students will make, and I'm sure some of you can see it right away. When you subtract, what do you need to do? You need to throw in a pair of parentheses because you're subtracting each term. When you're subtracting each term, that's going to change the signs. Okay? So some people like to rewrite it like me, because I, on occasion, make mistakes. It is very rare, but it has happened. Okay, so when I subtract them, I now get negative 5x to the third. I did that one. Plus 2x squared, it's positive. Plus 3x. Plus 3. Adding and subtracting is not that difficult. Okay, the next thing they want us to do is they want us to find the degree of f of x times g of x. They're not asking us to multiply, although we could, easy enough. You would just double or triple distribute depending which one you put first. To find the degree, let's think about where the degree is going to come from. The degree is going to be your highest exponent. Well, won't the highest exponent come from multiplying this term, this 2x squared, times this term, which is the largest in the second function, 5x to the third. I'll get 10x to the, what do you do when you are multiplying exponents? You add the exponent because that's the same thing as x times x. This is the same thing as x times x times x. I have a total of 5 now. So that will be the biggest exponent that should show up when I multiply those two functions. So the degree should be 5. What will the leading coefficient be? Well, the leading coefficient goes with where that degree is. It should also come from multiplying the largest degree term in each function, each polynomial, and we get 10. Okay. They want to generalize the steps of 2 and 3. Okay. The degree of the product of two polynomials is the sum of the degrees of the polynomials. That's what we did. We added the 2 and the 3. The leading coefficient is the product of the two polynomials is the product of the leading coefficients of both those polynomials. I would write that rule down. It might be handy to have. Okay, let's talk about composing functions. And some of you are like, oh my gosh, composing functions, it's been so long ago. Okay. Oh, I should have wrote down f of x and g of x. F of x was 2x squared plus 3x plus 4. 2x squared plus 3x plus 4. G of x is, oops, wrong way, 5x to the third plus 1. Okie dokie. They want to know what the degree of this is. Write an unsimplified version for f of g of x. Okay, I can write unsimplified. It's not difficult at all here. F of g of x looks like this. So we're going to take g of x here, and I'm going to insert it in parentheses. I hope you guys remember how to compose things. 5x to the third plus 1. This is a set of directions telling me to go to function f, plug in 5x to the third plus 1 wherever I see an x in that function. So I have 2 times 5x to the third plus 1 squared plus 3 times 5x to the third plus 1 plus 4. They don't want us to multiply that all out, which is good. They want us to predict the degree though. Okay, well, where's the degree going to come from? The degree is going to come from this piece here, because I'm going to take this 5x to the third, I'm going to end up squaring it, which will give me what? 25x to the 6, and it will also be multiplied by 2. That'll be the biggest. The degree will end up being 6, and that leading coefficient will end up being 50. Nothing will be bigger than that. When I take 5x to the third and squared it, everything else will be a lower degree. It will never get bigger, so that's where that's coming from. Expand it on a calculator. You guys can't do that, so we're not going to do that. Connie can do it, but no one else can. And then they want us to generalize the results of steps 1 and 2. Here's their generalization. The degree of the composite of two polynomial functions is the product of the degrees of the polynomial functions. The leading coefficient is the leading coefficient of g of x to the power of the degree of f of x multiplied by the leading coefficient of f of x. This is ridiculous. The math we just did was not that difficult. Why would I make a generalization about this? Sometimes it's best not to generalize things and just to work it out and find the answer. If you want to write the sentence down, you can, but I think it's very confusing, so I would not if it was me. Okay, so here are the general rules for this section. Sums, differences, products, and powers of polynomials are still going to be polynomials. You can find them easy enough by adding, subtracting. Remember to distribute the negative sign. Multiply, where you'll double or triple distribute or more, and you could take them to powers themselves. Step 4 from the activity tells us how we can get a degree by doing this. You might have to add the degrees, you might have to multiply them. And when you take the composite of two polynomial functions, we're still going to get a polynomial function. It just will be of a larger degree. Okay, so last example here. I think, yes. We are going to find the degree of f of x times g of x. I don't actually have to multiply them. I can if I want to, but the degree is just going to come from multiplying those two large terms in the each polynomial. So if I take 3x squared times 4x, I'll get 12x to the third. That tells me the degree is going to be 3. The leading coefficient, we already figured that out, will be 12. The degree of f of g of x, I'm actually going to write this down. F of 4x minus 5. Tells me to go to function f and plug this in. There's no reason to take it all the way out and simplify it though. 4x minus 5 squared plus 2 times 4x minus 5. Truthfully, there's no even reason to write all this down because everything that I need is going to be right here up front. I'll take this 4x and square it because that's where the large exponent is going to come from. 16x squared. That'll be taken times 3 though. So the degree is going to be 2. And the leading coefficient is going to be 16 times 3, which is 48. And that'll do it for us. Okay, I have to remember to make you a worksheet for tomorrow, and we're going to do some book problems. Go ahead and jot those down so you have them handy. And I will talk to you later. Goodbye.